So when we start with vibratory system, so the first thing we do is the free undamped vibrations. So free undamped system. So free undamped system refers to the mass and spring system. So I think I'll start recording the session. All right. So free undamped refers to the mass and spring system. So for any vibratory system, so first thing what we need to do is we need to come out with the general equation of motion. So general equation of motion. So for a free undamped vibration, okay, involving the mass m and spring stiffness constant k. Okay, so the general equation of motion we can write it as m x double dot plus kx is equal to 0. So this is a second order homogeneous differential equation because the right hand side is 0. That's why it is a free. Undamped because there is no damper here. So only we have mass and spring system. So for a free undamped system, so we can write the natural frequency of the system. Okay, so the natural frequency, we can write it as omega n. So omega refers to the circular frequency or the radial frequency. So we can write this as k over m. Okay, so it helps you to when you write down these equations several times, you feel more comfortable. So that's why I'm just keep writing here so that you will also note down these things. And these are some of the equations which will be useful readily for you when you do your class test, online class tests in the coming week. All right. So for the free and damped system, so we can write the general solution. So general solution means we need to write the displacement of the system. So in terms of the system parameters, that is the mass and the spring constant. So we can write the general solution in different forms. Okay. So simply we can write x, the displacement, as a function of time. Okay, so you can write a constant, let us say c. Then we can write in terms of the periodic function sine. So we can write omega n t plus phi. Okay, so we can also write this general solution involving sine and cosine terms. So for example, we can write this as a cos omega n t. Okay, so plus b sine omega n t. Okay, this format is also okay. So when we write in this format, so the c can be equated with a square plus b square under root. Okay, and the phi, the phase of the system, we can write it as tan inverse of b over a. All right. So this is for a free undamped system. So free undamped system. Then we can introduce for this system the damper. Okay. So when we have the damper, then we can call the system as free but damped. So we can call this as a damped free vibration. So the next system we can talk about is the damped free vibratory system. So in this case, we have the damper. So we are introducing the damper. So the mass will be there, then the damping constant C will be there. Okay, and the stiffness constant K will be there in the system. So for this system, we can write the equation of motion, general equation of motion. So this equation of motion we can derive using Newton's law by drawing the free body diagram, or we can also use the energy method. So the total energy, we write the expression and we take the time derivative of the total energy and equate it to 0. So once you simplify that, then we'll get the equation of motion. So in this case, the equation of motion will be, so we can write m. So I'm writing y double dot here. So this is the displacement in the y direction plus c y dot. So y dot is velocity here. Y double dot is the acceleration. So plus k y is equal to 0. So this is the general form of the equation of motion. Having a damper and a mass and a spring system. So for this system, again, we can write the natural frequency of the system as k over m and the square root. Okay. Now the general solution for this, we can write it. Okay. So the general solution for this, so we can write in different formats. So the first one, we can write it as the displacement as a function of time. So capital X is the amplitude of the vibration. So capital X multiplied by, so exponential power. So here we are having the damping constant eta. So eta into omega n t, then multiplied by, so I take out this, then we can just write sine the damped natural frequency omega d. So because we have a damper, so the frequency changes. So this is the damped frequency. So plus 5. So this is in one format we can write x, the amplitude, exponential power minus eta omega n t. So eta is the damping ratio. Okay, omega n natural frequency time, then sine omega d t plus 5. Okay, so we can also write this in a different format. So we can write, you can consider this is writing one way. So in another way, we can write this as the displacement as a function of time. Then the x, the amplitude again, the maximum displacement. So when I say amplitude implies the maximum displacement, then exponential power minus eta, the damping ratio, natural frequency, time, omega n t. Then you can write sine. So now instead of omega d, we can replace this with square root of 1 minus eta square, okay, into natural frequency. Okay, so omega d is nothing but omega n into square root of 1 minus eta square. So plus 5. So here everything is written in terms of the natural frequency. Okay, and we can also write in slightly different format, including both cosine and sine terms. Okay, so you can consider this is the third form. Okay, so again we write the amplitude or the maximum displacement, exponential power minus eta omega n t. So here we are going to write both cosine and sine terms. So we can write a constant A, then cosine omega d, this is the damped frequency, okay, plus B sine omega d t. So here there's no phase involved here, okay. So for a damped free vibrations, so the response or the general solution can be written in any one of this format. So when we talk about the damped free vibrations, the important part is this damping ratio eta. Okay. So if you note it down, then can I take this out, guys? How about others? Can I take this out? All right. So there are only two people present. Noor, Azhar, and all right, all right, Michael. All right, Vinod. Okay, so I take this out. Thank you. Then, uh, what did you miss, Michael? So you want to take note anything? The the first portion on top. What? All right. All right. So then we move on to the important part when we talk about the damp-free vibration. So the important thing is the damping ratio, eta. So eta is the damping ratio. So we can write this as C over damping constant, critical damping constant. Okay, CC. Okay, and this critical damping constant CC. So we can write it as 2m and natural frequency omega n. All right, and we can also write this as 2 square root of km. Okay, and you can also write the C over m as 2 times the damping ratio into natural frequency omega n. Okay, so when we have a damped free vibratory system, okay, the vibration is possible only in underdamped case. So the most important part is underdamped case. So in an underdamped case means the damping ratio is less than 1. Okay, so for underdamped case, the damping ratio is less than 1. So when the damping ratio is greater than 1, it is overdamped. So that means no vibration. Okay, and similarly, when it is equal to 1 damping ratio, we have the critical damping case. So even in critical damping case, so there is no vibratory motion. So the only case is underdamped case when the ratio is less than 1. The damping ratio is less than 1. So in this case, we can define the damped natural frequency omega d. So this one we can write it as omega n into square root of 1 minus eta square. Okay, so this is for underdamped case. And in this case, we can also write the period, damping period, tau d. Okay, so this is the damping period. So what is period? So period is the time taken for two successive vibrations, for one complete vibration. So the time taken for one complete vibration. So we can write the damping period tau d as 2 pi over omega d. So omega d we can replace with the natural frequency. So we can write omega n into 1 minus eta square. Okay, so these are the important things to note when we are dealing with damped free vibration. So under this, underdamped case is important, and the damping ratio is C, the damping constant, over the critical damping constant. So from this, we can relate this damping ratio, which is important in analyzing the damped free vibrations. Okay, yeah. So if you see the response which we have done for the damped free vibrations, so the eta is by far the most important part. So you can see eta is coming in all the forms of the general solution. All right. So now when we are dealing with the damp-free vibration, we when we are experimentally studying a system, okay, so we study the response of the system. So you have a system, let us say you want to study the response of the system. So what we study from the response is the logarithmic decrement. So logarithmic decrement. So we write the logarithmic decrement with the letter delta. So we define this as the natural log, uh, the ratio of two successive amplitudes. Say we can write log x1 over x2. So x1 is the amplitude of the first vibration, x2 is the amplitude of the succeeding vibration. Okay? So this logarithmic decrement we normally study from the experimentation of the system, okay, and we trace the response of the system. So once we trace the response means vibratory response, so we'll have the amplitudes with respect to time, how the amplitude is changing with respect to time. So therefore we'll be able to measure these successive amplitudes, and thus we'll be able to know the logarithmic decrement from the experimentation. Okay, so this logarithmic decrement is related to the damping ratio. So we can write this as 2 pi eta, okay, over 1 minus eta square. Okay, so that means by measuring logarithmic decrement, so we'll be able to find out the damping ratio. So we can also write when the damping ratio is small, when eta is small. So square root of 1 minus eta square will be very close to 1. Okay, when eta is small, eta square will be much smaller. So 1 minus, then if you take the square root, so basically we can equate square root of 1 minus eta square as 1. So we can write delta, the logarithmic decrement, as 2 pi into eta. So this is only when the damping ratio is small. All right, so we have seen all these things in the last session. So this is just a quick recap. So after the free damp free vibration, so now we can have uh, forced vibrations. So when we study the forced vibration, so that means we are dealing with external forces. So forced vibration. So again, we can study the forced vibration as undamped. That means without damper. Okay. Then you can also study damped. Okay. Introducing damper, but you have an external force to facilitate the vibrations, or it is part of the vibratory system, external force. So here the force, which is the vibratory force or the external force, so we can write this as a harmonic function again. Okay, so this is a repetitive force. So this repetitive force, we can write it as F naught sine omega t. Okay, so F naught is the amplitude of the force. So that is the maximum force. And this force is a function of time t. Okay, so the force varies with respect to time t, and the maximum force or the amplitude of the force is F naught. Omega is the external frequency with which the force is acting. Okay, so when we talk about undamped forced vibration, so when we take undamped forced vibration, so we can write, so F naught is the force amplitude. So we can also write maximum force. Okay, so omega is the external frequency. So external, you can say force frequency. All right. So when we talk about the undamped forced vibration, so the equation of motion involves, so the equation of motion will be So for free vibration, the right-hand side is 0. So now for forced vibration, so we can write my double dot plus ky. So we can equate this with f naught sine omega t. Okay. So this is again the second order differential equation. Okay, so we can also write this in different formats, but mathematically all the formats will be same. So for example, we can write this as y double dot plus k by m into y is equal to f naught over m sine omega t. So dividing every term with m, so we can write this. So the first term m gets cancelled, so you have y double dot. So the second term k by m into y. So the right hand side you have f naught over m. So now we can also write this as y double dot. So k by m, we know omega n is equal to square natural frequency, square root of k by m. So therefore, omega n square is equal to simply k over m. So we can replace k over m with omega n square y. So we can also write this as f naught over m into sine omega t. Okay, so don't get confused when you find the equation of motion in different formats. So basically, this is in the standard format, so we can write in different ways. Okay, so the response for this, you can write the response of the system. So since we are using the displacement as y, so you can write y is equal to, so it has two components, okay? So the first one, we'll have the complementary function, okay, considering the right-hand side is 0. So when we do that, the standard form of the response will be A sine omega t plus B cos, okay, I write omega and t. Okay, so this is considering the right-hand side 0. Then once we have the particular integral, so the solution we need to add for this part, then that will be, so we can write f naught over k. So 1 minus r square sine omega t. Okay, so the solution now, because of the force element, so we'll have the additional response. All right, so here the r is the ratio of frequencies, so we can write omega over omega n. Okay, so we'll be dealing with this ratio of frequencies quite frequently. So because this r, the ratio of frequencies omega over omega n, will be an important factor in the analysis of the forced vibrations. So because you have an external frequency and natural frequency. So this R plays an important role in the analysis of the forced vibrations. Okay, R is the ratio of frequencies. All right, so this is basically the undamped forced vibration. So the equation of motion can be written in different formats. So basically, the right-hand side, the force function comes. Okay, we are dealing with only mass and spring system. Okay, there's no damper. Okay, there's no C. So that's why we don't have the damping ratio here. All right, so for this, the natural frequency is omega n. Then the response we can write the response for the when there is no force complementary function. So the response is we can write like this. This we have seen earlier, similar response. Then for the force part for the particular integral, so this response will be f naught over k 1 minus r square into sine omega t. So where this R is the ratio of frequencies, external frequency and natural frequency. All right. So I take out this. Can I take this out? All right. Okay then. Okay, so we are now discussing the force vibration. Now we just looked into undamped force vibration. So now let us look into damped force vibration. So we take damper also, damped forced vibration. Okay, so we can write the equation of motion for this. So the general equation of motion, we can write the mass into acceleration plus c into v. V is x dot. Okay, plus the spring force kx. Okay, so we can write f naught into sine omega t. Okay, so this is the general equation of motion for the damped forced vibration. So damped and forced vibration. Now for this, we can write the response. Okay, so we can write x as the amplitude of the forced vibration. So if we consider x as the amplitude of the forced vibration, so we can write this x as, okay, so the force component, external force F naught, okay, over k minus m omega square whole square plus c, the damping constant omega square square root. Okay, so the amplitude can be written like this. Okay, so amplitude is part of the response of the system. Okay, so the phase phi can be written as tan inverse of c, the damping constant, omega, the damping ratio, external frequency, k into m omega square. Okay, so when we are discussing the damped and forced vibration, so an important part is we want to know what is the magnification factor. So magnification factor, or we also call it as amplitude ratio. So what does this means? So due to the external force, so how much are the amount of increase in the amplitude, what is the magnification in terms of the amplitude of the vibration? Because here the vibration is supported by an external force. So what is the contribution of this external force in terms of increasing the amplitude of the damped forced vibration, or it may be a damper also, it may be decreasing also. So here, the magnification factor, we simply can write the ratio of the two amplitudes. So x is the amplitude of the forced vibration, then due to the external force, the amplitude, we can write it as f naught over k. Okay, so this we can write it as x into k over f naught. So this is the amplitude ratio or the magnification factor. So this one we can write it as 1 over 1 minus r square whole square plus 2 eta r whole square under square root. Okay, so where, again, R is the ratio of frequencies, omega over omega n. Okay, so this is an important expression to know the magnification factor, or what is the increase in the amplitude due to the external force which is contributing to the vibration. Okay, so the phase, we can calculate the phase as tan phi uh, as 2 eta r over 1 minus r square. So this, okay, phi, you can write it as tan inverse of the whole thing. Okay, so tan phi can be written as 2 eta r over 1 minus r square. All right, so all these things we have discussed in the last 3 sessions. Okay, any questions so far? Let me know. Guys, any questions? All right, so if you have no questions, then the next topic which we'll be discussing is again the force vibration. But we study this force vibration, okay, not due to an external force, but this force vibration is due to the base moment. So with base moment. So here the force vibration is caused by the movement of the base of the system. All right. So I use the slides from here onwards. So this is precisely the topic 4. Okay, and this is quite important. So we are still hearing about the devastation in Turkey. Okay, so we can get some idea about why the vibrations or the earthquakes, which actually sends vibratory waves or the seismic waves and cause lot of destruction. And some places the destruction becomes much more. Okay, and some places the same amount of magnitude of the earthquake can cause little damage. It all depends on the building technology and also on the ground conditions there. Okay, so now let us study about this forced vibration, but with base moment. Uh, what is meant by this? As you can see, so the vibration system basically influenced by some reference point within the system. Okay, this is mostly by the motion of the base. Okay, so you can see the base motion is the forcing function. So in the next slide, we see what exactly is this base motion. So for example, if you think of a forging hammer, so a forging hammer transmits vibrations to the base, right? Okay, the vibration is generated by, it can be generated by various reasons because of the rotating centrifugal force or because of the reciprocating masses of the hammer. Okay, so basically there will be a base motion which is equivalent to the external force. Okay, just like a force vibration, but the force vibration is coming because of the movement of the base. Okay, so the floor vibration or the base vibration can then be transmitted to an instrument through its support. So this basically the movement of the base is transmitted through the instrument throughout. So this vibration transmissibility is very practical importance, and we need to study this so that we can understand how we can avoid this vibration transmissibility. Okay, so how to solve this vibration transmissibility? So the vibrations pass through the system from the base. So of course, the most important part is you need to come out with an intelligent design. Okay, is important. So intelligent design means you need to understand how the vibratory systems function. So we need to characterize the system parameters. That means you need to choose appropriate mass, strictness, and damping constant. So either theoretically or by experimentally. So that means to minimize or to avoid transmissibility of the vibration. So you need to design the vibratory system effectively by choosing appropriate mass and stiffness and damping factors. Okay. So later we understand if you can just increase the damping constant, you may not be reducing the vibration. So increasing the damping constant is not a solution. Okay, so there must be a proper mix of these things. So the amount of mass or the stiffness or constant or the damping constant must be appropriately chosen based on theoretical considerations. Then, of course, we model the system. Okay, so then we study the equation of motion, we study the response of the system, then we understand, so what are the natural frequencies? Okay, and we study these natural frequencies and we equate with the external frequency omega. Okay, so we try to avoid omega, the external frequency, equaling to the natural frequency of the system. So when omega becomes omega n, the external frequency equals to the natural frequency. So we know that the resonance takes place, and in resonance, the amplitude magnifies. So that means the vibration becomes much more violent in terms of the amplitude. So amplitude actually doubles. Okay, then basically we model the study system and we do the mathematical analysis of the model, and based on the assessment then we can see which type of parameters need to be adjusted, and we can identify the best possible system to isolate external vibrations. Okay, base transmission. Now, let us go through this here. For example, now the first one you see here, a machine is bolted to a rigid floor here. Okay, the machine is bolted to a rigid floor, and there's an input force here. So, okay, so the machine is subjected to an input force. As a result of this input force, okay, there is a transmitted force equivalent to the input force. So we know that the forces do not exist as singles. So forces always will be in couple. So from Newton's law, we know every force has an equal and opposite force. So when the machine is supported with an external input force, then the machine is fixed to the base, okay? And the base also transmits the equivalent force. Okay, so the machine is bolted to the foundation, and then if you want to isolate part of the transmitted force from the base, so what you can have is, so in part B you can see you can support the base with some isolation springs. Okay, so you can reduce or you can minimize the transmission from the base by having these isolated springs. So if you want to further reduce the or isolate the vibrations, then the third part is you can so create an inertial block. So So the machine is attached to a block, and the block is
An
supported
explosion of
by
child.
the isolator springs. Okay, so this way the vibration coming from the base transmitted force can be minimized or isolated. Okay, so this type of things requires when the buildings are built, in foundations. So normally in earthquake prone regions, they make sure that the seismic waves or the earthquake waves coming from the interior of the earth, so they have minimum effect on the building. So there will be a seismic factor incorporated in the basement. So there will be the base is the mass is supported, or the building is supported by the springs. Then there is a seismic mass which can absorb a lot of the energy which is coming from the uh, okay base. And again, this seismic mass is supported by the isolator springs, and then you have this building or whatever the mass here. Okay, so this way it is possible to isolate the effect of the base functioning, okay, causing transmitted forces on the machines. So this type of technology is used in many parts of Japan. So when they construct huge buildings, and thus they avoid the collapse of the buildings. Okay, particularly when due to high magnitude earthquakes. All right. So next we move on to the theoretical aspects. So we study now this base movement. So now we are going to analyze the force vibration with the base movement. Okay. So here the force is coming from the movement of the base. Okay. So here we consider the y as the displacement of the base. Okay, now you can consider the system, mass, spring, and damper system. Okay, like this. Okay, now the system is connected to a base. Okay, mass, stiffness constant, and the damping constant. Okay, a damper and a spring with a mass connected to a base. So the base here, the displacement of the base, okay, can be given as a harmonic function again. So the displacement of the base varies with time. Okay, capital Y is the maximum displacement. Capital Y is the maximum displacement. So basically, we are writing that the displacement of the base is harmonic function like this. Okay, it varies with time. So the maximum amplitude of the base is y. Okay, so x is the displacement of the mass. So x is the displacement of the mass. So x is the displacement of the mass, y is the displacement of the base. So y, the displacement of the base, we are writing as a harmonic function like this. Okay, where capital Y indicates the magnitude or the maximum displacement of the base. And this displacement varies with respect to time. So at any time t, the displacement y is given as capital Y into sine omega t. So now this is the vibratory system. So the mass is inertia mass. So it is subjected to acceleration. So the spring is connected to the base and the mass. Okay. The displacement of the base is y. The displacement of the mass is x. So the spring force will be k times net displacement. So the net displacement, we can write it as x minus y here. Then for the damper C, okay, so the force acting on the damper is C into the velocity. Here the velocity of the mass minus the velocity of the base, so the differential velocity. So we can write this as C into x dot minus y dot. So the force due to the mass and acceleration is upwards. Okay, the spring force and the damping force will be downwards as shown here. All right. So, so now we need to write down the equation of motion for this system. This system is different from the forced vibration, because here the forced vibration is caused by the movement of the base. Okay, so the movement of the base we are now writing in terms of the displacement of the base. Okay, and this displacement is also we are writing as a harmonic function. So this is the free body diagram for the system. Now we can apply the Newton's law, then we can write the net force acting on the system. Now the force, you can equate these two forces, okay? The forces are equal and opposite. So we can write mx double dot. So you can write this is equal to negative of k into x minus y. So instead of negative k, so we can write k into y minus x, okay? So similarly, C into x dot minus v dot negative. But we can write the same thing as plus y dot minus x dot. So change in velocity. So now you can elaborate this. So multiply k with y, ky minus kx plus c into y dot minus c into x dot. So we can rearrange this term. So you bring your cx dot the other side, then kx the other side. So you will get the equation of motion as like this. Okay, mx double dot, that is x double dot is the acceleration, cx dot, x dot is the velocity, plus kx. So kx is the spring force, x is the displacement of the mass. So this one we can write it as c into y dash. So y dash is the velocity of the base. So if y is like this, so y dash will be the derivative of this y. So you can simply write omega y. So sine omega t becomes cos omega t. So you can write cy. Okay, so y dot becomes omega y into cos omega t. Okay, so you can replace this y dot with c y omega cos omega t. Y dot is replaced with omega y cos omega t. Then y is replaced with y into sine omega t. So therefore, you can write the equation of motion for this as mx double dot plus cx double dot plus kx is equal to, so you can write simply as cy dot plus ky, or so you can elaborate the first derivative of y, the displacement of the base. Okay, you can write either way. So this is basically the equation of motion for the um, damped system with base moment, with the moment of base. Okay, so here the base moment we are taking as a function of a harmonic function. So the moment of the base varies. All right, guys, any questions on this? So deriving the equation of motion for the forced vibration, and here the vibration is due to the movement of the base. Any questions? All right, Shashi. Then we'll move on to the next part. Next part is the finding the response of the system. Okay, so the right hand side of this previous equation, so this portion, the right hand side, so you have cos omega t, sine omega t. Okay, so we can write the response. Okay, we can write this as a1 cos omega t and a2 sine omega t. So what is a1? So a1 can be, so here the a1 is simply, you can write it as a1, and a2 is this. Okay, so you can write this as A1 cos omega t plus A2 sin omega t. So that is what is shown here, A1 cos omega t and A2 sin omega t. Okay, and this one you can write it as with one constant A. So you can write it as A sin omega t minus alpha. So here alpha is nothing but again phase. Okay, so sometimes we write it as pi or sometimes alpha. Okay, so here the A now we can write it as square root of A1 square plus A2 square. Okay, so we have seen this derivation for A. We have seen this under forced vibrations. Okay, and for the phase. Okay, I gave you this equation. So we discussed this equation in the last session. So the same equations are shown here. Okay, so the right hand side of the equation of motion we can write in as A sin omega t minus alpha. So where A can be written like this and alpha can be written like this. Okay, and this A corresponds to the harmonic force of the magnitude A. Okay, so this magnitude A corresponds to the force F naught when we discussed the force vibration F naught sin omega t. So F naught is the maximum force or the amplitude of the force. So then you can write the steady state response for the uh, displacement of the mass. Okay, x is the displacement of the mass. So how this displacement varies due to the force. So the steady state response, we have seen this expression for the uh, damped forced vibration. Okay, so now we can replace this F naught with A. So this is from the session 3 where we have seen for the damped and forced vibration, the response of the system. Okay, so now replacing the force F naught, okay, with okay, so F naught is A, so A is this y into square root of k square plus c omega square. So once we replace this, then the displacement of the system for the base moment, okay, due to the base moment, okay, the displacement of the mass due to the movement of the base x can be given like this. Okay, so here y is the displacement of the mass. Okay, the block, the base. Y is the displacement of the base. So x is the displacement of the mass. So from here, the magnitude or the amplitude of the response x, so the maximum value of this x, okay, happens when this is 1, okay, when sine theta is 1, okay, so x will have the maximum displacement. So the maximum value for sine omega t minus phi is 1. So therefore, the amplitude can be just written as by considering this factor as 1. So we can write the amplitude as only this portion. So y into square root of k square plus c omega square over square root of k minus m omega square plus c omega square. So this is the expression for the amplitude of the movement of the mass. Okay, and y is the amplitude of the base. So now if you take the ratio of these two, so you get amplitude ratio x over y. So x over y can be simply written like this. So that means due to the base moment with amplitude y, okay, so the amplitude of the mass, vibratory mass x, so the ratio depends on this particular expression. So where k is your stiffness constant, so c is your damping constant, and omega is the external force here. Okay, uh, that means the vibration, the frequency of the base movement omega. Okay, external frequency. So m is the mass. Okay, so that means due to the base movement, we can write the amplitude ratio x over y. So x is the displacement or the maximum amplitude of the mass in the vibratory system. So y is the amplitude of the base. So the ratio of these two amplitudes, so we call it as the amplitude ratio. So the amplitude ratio now, theoretically, we can prove that it depends on this expression. Okay, so just to reinforce the concept, so now you need to see y is the displacement of the base. Okay, so x is the displacement of the mass. So base you have, okay, mass is part of the vibratory system. So the magnitude of the displacement of this mass over the magnitude of the base. Okay, so this ratio we call it as the amplitude ratio. So what is the amplification factor due to the base movement? So that causes the displacement of the mass. So this portion we can prove that it is amplitude ratio is x over y. So it depends on the stiffness constant, then the damping constant, and the um, uh, amplitude variation of the base, the frequency of the amplitude of the base omega, okay, the mass of the system. Okay. Okay, so this is an important expression when we are dealing with the post vibration due to movement of the base. Okay, so now we can study the response of this. So how you can say the same, guys, please note down this equation. I clear this first. Okay, so now this equation can also be written, okay, is identically equal to this expression. So this expression is easy to note down, easy to memorize. So we can write now x over y as, okay, uh, 1 plus 2 eta r. I'm sorry. So 2 eta. So omega over omega n, you can write it as r, so whole square. Okay, over 1 minus r square. So this is the same equation which we have seen for the damped forced vibration. So 1 minus r square. So you can replace this, so omega over omega n with r. So replace with r. So the equation looks in a simplified manner. So plus 2 eta r whole square. Then you need to take the square root. Okay, you can see the square root is for the entire thing. So both the equations which you see here, okay, when you replace with omega over omega n, okay, then you will get this with the damping ratio and the frequency ratios. And this expression, okay, we have seen the, yeah, alpha, the phase, you can write it as tan inverse of c omega over k negative. So the same thing can be written like this. So I clear this. So you can also write the phase response. We can write this way. Okay, so when we are talking about the base movement, Okay, and how this base movement, displacement variations in the movement of the base causes a damped force vibration. Okay, the amplitude ratio can be written like this, and the phase of the response can be written like this. Now, we can also call this x by y, okay, as the displacement transmissibility of the system. Okay, so how much amount of displacement of the base is transmitted into this system. So that is the displacement transmissibility x over y. So we can call x over y as the amplitude ratio or the displacement transmissibility, and we can also write this as the force transmissibility. So because displacement is proportional to the force, right? So we can also write this as the force transmissibility of the system. So how much amount of displacement from the base is transmitted through the vibratory system, damped vibratory system, or how much amount of the force from the base is transmitted to the system. So that is the displacement or the force transmissibility of the system. So these two expressions will tell us the force transmissibility and the phase response of the system. All right. So now we pay attention to the figures here. So here you can see this is the displacement transmissibility or x by y, the magnitude. Okay, so the magnitude is taken. So you can see the x-axis is the frequency ratio. So a plot frequency ratio versus the displacement transmissibility is gives maximum displacement when the frequency ratio is 1. When the frequency ratio is 1, so you can see the displacement transmissibility is maximum. So this is because the resonance conditions. So when the frequency ratio is 1 means omega is equal to omega n, the natural frequency of the system. So that means the resonance is taking place. So during resonance, the amplitude ratio or the displacement transmissibility is maximum. So for different types of damping ratios, whatever may be the damping ratio. So here the damping ratio is 1.0.25, okay? All right, that is the first part. So when the frequencies equals, so the resonance conditions takes place. Other than that, you can see what is happening when the frequency ratio is equal to square root of 2. So you can see this is the portion. So when the frequency ratio is square root of 2, so you can see that the transmissibility is 1. Displacement transmissibility is 1. Okay, and if you really want to reduce the displacement transmissibility, okay, so that means the frequency ratios must be very high. So that means omega over omega n should be greater than 2. Or you can say that omega should be much greater than omega n. So when the frequency, external frequency is greater than the natural frequency of the system, so you can see the amplitude ratio is below 1. Okay, so the amplitude ratio depends on this frequency ratio R. So if you want to minimize the displacement transmissibility, so you need to make sure that the external frequency is much greater than the natural frequency. Okay, irrespective of the damping ratios. So irrespective of the damping ratios, so you can see when the frequency ratio is greater than 2 or for higher frequency ratios, okay, the displacement transmissibility is below 1. So below 1 means, uh, the transmitted force is less than the external force. All right, guys, any questions on this? Any doubt? So the frequency ratio plays an important part in understanding the systems. So one main purpose is so to avoid this displacement transmissibility or force transmissibility to reduce. So if you want to reduce force transmissibility, so one of the criterion is this external frequency should be much greater than the natural frequency. So therefore the ratio of frequencies will be higher. Okay, so this figure basically tells out how the phase angle varies with respect to the frequency ratios. Again, when the frequency ratios is equal to 1, the resonance conditions take place. So you can see the frequency phase angle is about 90 degrees. Okay, and the phase angle increases for higher frequencies. Okay, so depending on the damping ratios. All right, so we can read the description of this, the interpretation of this curve. So we can also call this displacement transmissibility as the force transmissibility. So what is the amount of force transmitted over the magnitude of the force? So the ratio is identically equal to the displacement transmissibility. Okay, so force transmissibility, because force is just displacement, it is proportional to the displacement. So therefore, we can write down that force transmissibility as equivalent to the ratio of displacement transmissibility, x over y, the magnitude. So take only the magnitude. So you can see that from the transmissibility curves, okay, at frequencies when omega is greater than √2 omega n, okay, so the addition damping actually increases the transmitted force. So you can see, I just clear this. So at this point, when omega n is, the frequency ratio is √2. So you focus here, the frequency ratio is √2. Okay, so whatever may be the damping ratio eta, okay, so even if you are increasing the damping ratio, so you can see when this r is equal to square root of 2, okay, increasing the damping ratio is not having any effect on the transmissibility. So the transmissibility remains 1 irrespective of the damping constants. So that means if you want to increase the damping ratio, uh, it will not reduce the displacement transmissibility or the force transmissibility. So increasing the C value in the vibratory system is not a solution to reduce the force transmissibility. So because when this ratio is square root of 2 equal to square root of 2, so you can see the displacement transmissibility is 1, irrespective of the damping constants. Okay, so that point is mentioned. So as a consequence, normally we assume that adding a damping reduces the vibration problem. So if you actually adds more damping constant, the vibration may reduce, but the force transmissibility may increase. All right. So the force transmissibility is equivalent to displacement transmissibility. So we discussed the movement of the base, okay, when a vibratory system is connected to a base, and the base is having a displacement, right? So we theoretically studied the system, and I just quickly go through once again. So for a vibratory system with base movement, so we got the equation of motion for the system. So this is the equation of motion for the system. Now the response of the system, okay, the response of the system, we can prove that the response of the system X. So here there are two things. One is the displacement of the mass X. So the other one is the displacement of the base Y. So here the response for the displacement of the mass can be written like this. So where the amplitude of the displacement of the mass is, we can write like this. But the more important aspect for this is the amplitude ratio X over Y. Okay, so X is the vibratory system magnitude, Y is the magnitude of the base. So the ratio we can write by this expression, and this expression is identically equal to this one. Both are same. Okay, so X by Y is the response of the forced vibration with base movement. So the amplitude ratio or the force ratio. So you can see that here the important factor is the ratio of the frequencies omega over omega n. And the phase response for the system can be written like this. All right. So now let us go through this example. I pause for a minute. Any questions, guys? So let me know if you have any questions or anything. All right. So if you have no question, I'll just quickly take your attendance. All right. So let us go through this example. This is again from your learning materials. So we are looking at displacement transmissibility. So the following schematic is simplified representation of a vehicle traveling on a rough road. So here the base vibration is coming due to the undulatory movement of the road surface. So the road surface is not smooth, as you can see here. So there's a roadside surface is having a vibrate undulations, means the amplitude varies here, right, in a harmonic way. Now you want to study the variation of this amplitude on the road, okay, on a vehicle traveling, okay, and we can model the vehicle as a uh, undamped system, okay, so with a mass, stiffness constant, and a damper. So the parameters for the mass, the vehicle given, the mass is given 1200 kilograms. So the stiffness constant for the vehicle is given 400 kilonewton per meter. So the damping ratio for the system is given 0.5. Okay. And the vehicle is traveling at 100 kilometers per hour. So we can always convert this into meters per second. Now, under these conditions, you are asked to determine the maximum displacement amplitude of the vehicle. So, what will be the amplitude or the maximum displacement of the vehicle when the vehicle is transferring? moving with a 100 kilometer per hour speed with a mass of 1200 kilograms and a stiffness constant of 400 kilonewton per meter and a damping ratio of 0.5. Okay, so we need to find out the maximum amplitude or the maximum displacement x. Now the road surface varies sinusoidally with an amplitude of 0.05 meters and a wavelength of 6 meters. So the wavelength is given, okay, as 6 meter. So wavelength is basically the lambda, the distance. Wavelength is represented as lambda. So this is the distance on the wave at two successive points having the same phase. So that means you can say here from here to here. Okay, so this is the wavelength. So here the amplitude is 0, then again here the amplitude is 0. So amplitude going to positive, then 0, then negative, then okay. So lambda is the wavelength given as 6 meters. Then the maximum amplitude of this road surface is given as 0.05. All right. So now with this given information, so now let us try to find the, okay, based on the undulations given here, okay, the road surface, so we can calculate the frequency. Okay, so we know the frequency of the road, okay, the undulatory nature or the displacement variation frequency of the road as 2 pi f. So f is the frequency, natural frequency. Okay, so this one you can convert in terms of the vehicle speed. So what is the speed of the vehicle? So it is moving with 100 kilometer per hour. Okay, so convert into meters per second. So that will be 100 into 1000 over 3600. So this one, the frequency can be given as, okay, so velocity over lambda. Okay, if you have studied your secondary school or maybe the polytechnic physics, so we can relate the velocity of a wave with frequency and wavelength. Okay, frequency and wavelength. So velocity can be written as the frequency multiplied by the wavelength lambda. Okay, so here we know velocity and we know lambda, therefore we are calculating the frequency. Okay, so f can be written as v over lambda. So lambda is the wavelength, which is 6. Okay, so velocity of the vehicle is 100 kilometer per hour, so you convert into meters per second. So you're multiplying 100 with 1000 meters over 3600 seconds. Okay, so basically, so what you see, this portion is frequency f. So we are writing v over lambda. So this is the frequency of the base excitation, which can be found by dividing the vehicle speed by the length of the cycle road roughness. So that is the wavelength. So the wavelength of the frequency omega, we can write it as 2 pi f, and once you calculate, so you can see the frequency of the undulatory road surface due to the velocity of the vehicle is equivalent to 29.0887 radians per second. Okay, so we can calculate the external frequency. So in this case, the external frequency is due to the undulations on the road and due to the velocity of the vehicle. Then we can calculate the natural frequency for the vehicle, omega n square root of k by m. So k is the stiffness constant, which is given 400 kilonewton per meter. Okay, so mass is given 1200 kilograms. So once you calculate this, you will get the natural frequency of the system, of the vehicle. So we know the frequency of the base, that is the undulatory nature of the road. Then we know the natural frequency of the system, the vehicle. So then you can calculate the frequency ratios R. Okay, R is omega over omega n. So in this case, the frequency ratio is 1.5933. So then we need to calculate the amplitude ratio. So amplitude ratio is x over y. So we can use the standard formula. So as we have seen earlier. So here R is the ratio of the frequencies. Okay, so put everything here. Eta is given, the damping ratio. So once you put everything and calculate the ratio, you get 0.8493. Okay, so x by y is 0.8493, or you can write the amplitude of the vehicle, the vibration of the vehicle, x is equal to 0.8493 into y. So y is given as 0.05. So that means the amplitude of the displacement of the vehicle is 0.0425 meters. So that means when the vehicle is traveling at a speed of 100 kilometer per hour, and when the road is having a maximum displacement of, I'm sorry, okay, and the road is having a maximum displacement of 0.05 meters with a wavelength of 6 meters, then the vehicle will have a displacement of 0.0425 meters when it is traveling at a speed of 100 kilometer per hour. So in this case, the displacement amplitude ratio is 0.8493. Guys, any questions or anything not clear, let me know. So normally when we travel in a vehicle, so when you have the strips, speed reducing strips, so you can see the vibrations of this. We do feel some vibrations, right? And in this scenario, you can calculate that when the maximum amplitude of the road is 0.05, then the amplitude ratio is 0.8493, depending on the stiffness constant, mass, and the damping constant of the vehicles. Okay, the same thing can be reduced with more effective choice of mass, stiffness constant, and also the damping constants, damping ratio. So normally the sports vehicles and the more expensive vehicles, they'll try to reduce this amplitude ratio. So by choosing more appropriate um, damping ratios and the stiffness values and the damping constant values. All right. Let me know any questions or anything not clear in this example. So normally in the end of term exams, definitely there will be a question dealing with amplitude ratios or the force transmissibility. So any questions? All right, so Nuraja says no questions, then we'll move on to the next example. So in this example, we are going to do the force transmissibility. So what is the amount of force that is transmitted through the system? Okay, so here we are dealing with a machine having a mass of 100 kilograms, and this is supported by springs. The total spring constant is 700 kilonewton per meter. Okay, and it has an unbalanced rotating element. So here the force is coming due to a rotating unbalanced element. So when something is rotating unbalanced, so there will be a rotational force, okay, uh, which will be acting on the system. So which results in a disturbing force of 350 newtons at a speed of 3000 rotations per minute. So the force is 350 newtons when the speed of the unbalanced mass is rotational speed is 3000 rotations per minute. So you're asked to assume a damping factor of 0.2 or damping ratio. So under these conditions, you're asked to calculate the amplitude motion due to the unbalance and the transmissibility, force transmissibility, okay, and the amount of force transmitted. So the transmissibility is basically you're asked to calculate the ratio. Then part C, you need to calculate the actual amount of force that is transmitted. Okay, so this is the question which falls under the transmissibility. Okay, the base moment. Okay, so for the given case, we can calculate the static deflection of the system. So static deflection is mg over k. So delta is mg over k. Mg is the weight of the system. Okay, k is the stiffness constant. Okay, so k into delta. Delta is the deflection. So that is equivalent to weight. So once you do this, mass is 100 kg, mg 9.81 multiplied. Stiffness constant is 700 kilonewton per meter. Okay, so you can take it as 700 kilonewtons, 700 into 10 power 3. If you do this calculation, so the deflection, static deflection you get is 1.201 mm. Okay, so then you can calculate the natural frequency of the system. So natural frequency of the system, uh, okay, so this is whatever is the static deflection, G over static deflection. Okay, so G over delta stat. So here you're calculating 2 pi of omega. So you can write it as omega n. So you can just write this with a square root. So instead of k over m, so here because the force is due to the weight of the system, so you will have g over static deflection. So if you calculate here the frequency, this is cycles per second, okay, FM, not the circular or radial frequency. So it is just the normal frequency, cycles per second. So you can calculate the natural frequency of the system. Okay, so once you know the natural frequency of the system, now from the equations given, so you can calculate the amplitude response X. Okay, so this is F naught over K. F naught is the force. Okay, so K is the stiffness constant. Okay, so this one is F naught over K square root of 1 minus R. R is the ratio of frequencies. Okay, So 1 minus r whole square plus 2 eta r. Eta is the damping ratio. Okay, 2 eta r whole square. Okay, so this is F naught over K comes here. So this is the formula for the amplitude of the X. So if you take this F naught over K down, so then you will get, okay, from the calculation given, we know everything. R is the ratio of frequencies. Okay, so if you see the frequency we calculated is, I'll go back to the previous one. So the frequency we calculated is 13.32. Okay, so now this 300 rotations per minute is given as the speed of the rotational speed of the unbalanced mass. So you convert this omega, okay, rotations per seconds. So if you divide this 3000 over 60, you will get rotations per second. Okay, so that will be 50. So the 50 will be the this 50 is the frequency of the rotating mass. Okay, R is 50. Then the frequency of the rotating mass is 50, 3000 over 60. Then 13.32 is the frequency which we calculated. So based on the weight and the stiffness. Okay, so from this we apply the response, the amplitude formula. Then we can calculate the amplitude. So from this, the force transmissibility we can write. Okay, transmissibility or force transmissibility is the force transmitted over the magnitude of the force. Okay, so we have the formula for this, so you can just use everything in that, calculate, then you get the transmissibility ratio as 0.137. How much of the force is transmitted? So the force transmitted is, the magnitude of the force is 350 newtons. So multiply with this 0.137. So that means out of the 350 newtons of the force, so the system, the amount of force transmitted through the system is about 47.9 newtons. Is that clear, guys? Any questions? So we are applying the theory to practical cases. So we have done the two examples. The first one is the vehicle moving with a particular speed on a undulating road. Okay, then how much of the transmissibility is taking place in terms of the displacement. Now in this case, the force rotating unbalanced. So the amount of force is 350 newtons, okay, undesirable force. Out of this, then the amount of force transmitted through the system is because of this ratio. So you can see about 47.9 newtons. Guys, any questions, anything, any doubt? Noor Azhar is asking, where do we get 50? Okay, so the 50 comes because the you need to convert this 3000 RPM into RPS, rotations per second. Okay, so yeah, that's right, Azhar. So 3000 over 60. Okay, so this is per second, therefore you will get only frequency. So this is all right. Okay. Any other questions, guys? Any other questions? All right. So next we talk about this unbalance because of the rotating systems. So when a system is rotating, okay, uh, there will be unbalance in the system. Okay, simply consider. I'll just try to. So let us say, okay, yeah, okay. Let us say there is a mass, and let us say there is another mass. Okay, so the system is having a rotation. You can consider this M1, M2, and the system is in rotation with, let us say, angular speed of omega, but we consider that the net mass, if the combined mass of the system or the net force acting on the system is not zero, then there will be unbalance. So if the net force acting on the system is not zero, so then there will be unbalance in the system. So we are now considering an unbalance in the system due to rotating masses. We'll study this unbalance in a much more detailed way when you do mechanics of machines course. Okay, so now just to understand this unbalance, okay, of a rotating system. Okay. So you need to look at this figure. I just show you the figure. Okay. So there are two things which you need to know. Okay. So this is a small mass m. Okay. And the system has a mass capital M. Okay. So capital M is the mass of the entire system. Small m is the rotating mass here. So E is, okay, eccentricity we call it as. So from the axis of rotation, so consider this is your axis of rotation. So the mass m is placed at a distance e from the axis, and we call E is the eccentricity. Okay, so this small m is the unbalanced mass. Okay, so the entire mass of the system is capital M. So this is supported by the springs and also a damper. So basically, you have the damped vibration, but here the force is coming due to unbalanced force. Okay. So when a force is in rotation, so what will be the centrifugal force? So if a mass is rotating, so let us say the distance is r, m. Okay. So what is this force developed centrifugal F, normal force? Anyone? You must have done this in the dynamics course. What is the normal force developed here? Let us say the mass is rotating with angular frequency or angular velocity omega. Anyone? So what is the expression for the force? So we can write it as mass into normal acceleration. So a rotating mass will have acceleration directed towards the center, right? So what is normal acceleration? Anyone? I'll wait for your answer. Tangential acceleration will not contribute. So tangential acceleration will be in this direction. So this is the tangential. So normal acceleration you can write two ways: v square over r. But v is r omega. So therefore you can write this as m into r into omega square. Because velocity v is related to the angular velocity omega. V is equal to r omega. So the normal force, we can write it as mr omega square. All right. So now let us look at this system. So now what is given? So there are many machines. For example, a simple one about this rotating unbalance in our day-to-day life we experience from the washing machine. Okay, so particularly when you have the front load washing machines, so you can see when there is um, unbalanced mass, actually the vibration of the machine is quite high. So basically how the load is put into the machine is important, the amount of load. Now let us consider an unbalance in rotating machines. So we consider a mass and spring system with a damper. Okay. Now what is things to consider here is this is an eccentric mass m. Okay. So the eccentricity is the distance this mass is located from the axis of rotation. Okay, that is E. Okay, that is rotating with angular velocity omega. So the system is rotating with angular velocity omega. Okay, for this system, we consider x is the displacement of the mass. So x is the displacement of the mass here. Okay, so x, the displacement of the non-rotating mass. So the rotating mass is only small m. So the entire mass of the system is capital M. So non-rotating mass is m, capital M minus small m. Okay. Okay. So from the static equilibrium, we can say that the displacement of the mass m is, okay, the static displacement. So the displacement x plus, so eccentricity into sine omega t. Okay, so if you consider this is the angle theta, so omega t is nothing but theta. Okay, the angular displacement. So the total static equilibrium position, the displacement, we can write it as x plus into e sine theta. So theta is replaced with omega t. Omega is the angular velocity of the mass m, small m. Okay. So now for this system, we can write the equation of motion. Okay. Again, we draw the free body diagram. I clear this. Okay. Now for this system, we can the net mass acting on the system is m minus m. Okay, so this is the net mass. So mass into acceleration. Okay, then due to the displacement of this, so the second derivative of the displacement can be the acceleration, right? So the acceleration of the small mass is m x plus e sine omega t is the net displacement. So if you take the second derivative of this displacement, you get acceleration. So the force due to the rotating mass m, you can write as the d square over dt square over x plus e sine omega t. So x plus e sine omega t is the net displacement. So the net force acting on the system is the due to the non-rotating mass capital M minus m and due to rotating mass small m. So we can write both. Okay, this is the net force acting on the system. And the free body diagram here, so you have the spring force, so k by 2 you can add up. So the spring force is k into x. Okay, and the force due to the damper is c into v. Okay, so these two forces are equal and opposite. So the spring force and the damping force will go with negative sign. All right, so now we can expand this equation. So we can expand this equation, capital M into x double dot, we can write minus m into x double dot. Okay, so here d square x is nothing but x double dot, small x double dot. So m into x double dot. So then if you take e omega square sine omega t is nothing but your the centrifugal force. Okay, so I wrote that the force is m r omega square. So r is here is e. Okay, so omega square. So instead of mr omega square, we have me omega square. But this force varies with respect to theta. So that is omega t. So therefore, you can write the force is me omega square into sine theta. All right, so this one you can write minus kx into cx dot. So rearranging the terms, so you can write the equation of motion for this is mx double dot plus cx dot plus kx is equal to me omega square. So me omega square is the force. This force is not constant, but it varies with respect to the angular displacement, theta. Theta is omega t. So therefore, this portion you can simply write it as f naught sine omega t. So the unbalanced force F naught is me omega square. Okay, so this will be the magnitude when theta is equal to 90 degrees. So sine 90 is 1, so the maximum will be me omega square. All right, so this is a harmonic force, varies with angular velocity. So the maximum force is equal into me into omega square when theta is 90 degrees, that is omega t is 90. Okay, so for a rotating unbalance, this is what we can derive the equation of motion. Okay, so note down this equation of motion. And you can see that this equation of motion is the same as our damped and forced vibration. So this is the same as damped and forced vibration. So we can replace simply the F naught, the force, with me omega square. So therefore, for undamped rotating unbalance, the analysis is the same because the equation of motion is essentially the same as the damped and forced vibration. which we have already done in the last session. So therefore, we can write the amplitude of the magnitude of the displacement x is okay. So we can write like this. Then these equations we have seen earlier. Then the phase can be written like this. So we can treat this system as a simple damped and forced vibratory system. Okay, a simple uh, damped and forced vibratory system. The only difference is here the uh, force is due to a rotating unbalance in the system. So here the force is me into omega square. So E is the eccentricity of the system, m is the mass which is in rotation with angular velocity omega. Okay, and this force varies with respect to angular displacement. So therefore, we can write this as a harmonic function me omega square into sine omega t. So therefore, you can see the equation of motion is the same as a damped and forced vibration. So therefore, we can use the same analysis which we have done in the last session. So where the displacement can be written like this, then the tan phase can be written like this. So these two equations are exactly the same. We can take it from damped forced vibration. Okay, and in this case, the transmissibility of the system, we can write it as, okay, the force transmissibility or the displacement transmissibility. So the equation becomes like this. So here omega over omega n you can replace with the ratio of frequencies r. Okay, and the response of this system, so we can just follow the one which we have done for the forced damped vibration. Okay, this is the response which we have seen earlier, last session. Okay, so these are the displacement transmissibilities. This is the phase. So these equations will be exactly the same like the damped and forced vibration. Guys, any questions on this? So here again we can see the frequency ratio versus the amplitude ratio. Okay, and again when for resonant frequencies, when the ratio is 1, the amplitude displacement is maximum. Okay, amplitude displacement is maximum. And again, depending on the damping ratios, the amplitude ratios may reduce. So this is basically when you plot for various values of the frequency ratio and versus the damping ratio, the displacement transmissibility. So the characteristic curve look like this. All right. So the time is nearing 8:30. So we'll have a break now. Then we'll meet again at so 8:50. Is that okay? So we'll have a break now. All right. So guys, I'll see you at 8:50. Then we can go through some more questions, and I'll also go through your second assignment questions. Is that okay? All right, guys. Hi guys, hope you're back. Can you hear me? All right. Okay. Okay, guys. Then we'll continue. All right. So what we have done so far is that to just summarize, we have done forced vibration with base movement. That is the first part we have done today. The base vibration with okay, free vibration with forced vibration with base movement. Okay. So for this, we have derived equation of motion. Then we have seen the response of the system. So while finding the response of the system, so the useful quantity is to define amplitude ratio or transmissibility. Okay, so for this system, so we got the amplitude ratio formulas, and for the phase formulas, then the force transmissibility and amplitude transmissibility both are the same. Okay, then we have looked into a couple of questions. Then after that, we have looked into unbalance due to a rotating mass. So this is due to a rotating mass. The first part is due to the base moment. Okay, now here due to a rotational motion within the system. So due to unbalance in terms of the mass. Then the equation of motion we have derived. And once we derive the equation of motion, you can see this equation of motion is exactly the same as for the damped and forced vibration. So the equation of motion is the same as damped and forced vibration. So therefore, the response also will be the same. So we can pick up the responses for this from the previous analysis. Okay, so this is the transmissibility expression. This is for the phase, and the last one is for the response. Okay, all right. So next we move on to the example here. So this example is related to rotating unbalance. So what is given here is a 30-kilogram rotor. So this is the mass of the rotor given, the total mass. Is unbalanced such that its effect is equivalent to a 4 kilogram mass located at 60 mm. So eccentricity E is given 60 mm, okay, and the small mass, okay, E is 60 mm, and the unbalanced mass is 4 kilograms. So this is 4 kilograms. So 30 kilograms refers to the total mass. Okay. The system is supported by 4 springs with 200 Newton per meter. So you can add up that the total spring stiffness constant will be 800. Now, under these conditions, determine the amplitude of vibration when the rotor is turning at 10 radians per second. Okay, and the damping factor, the eta is given as, so this is damping ratio. Okay, so the damping ratio is given as 0.15. Okay, so here mass we know, eccentricity we know, then we know the angular speed, angular velocity. So therefore we can calculate the rotating unbalanced force. Okay, m e omega square. Okay, let us see the working. Okay, so the force you can calculate mr omega square or me omega square. 4 is the unbalanced mass, 4 kilograms. The eccentricity or from the axis of rotation, the distance of this mass is 0.06 meters, which is given. Then angular velocity of the system is given. So once you calculate this, the unbalanced force you get is 24 newtons. But since the unbalanced mass is in rotation, so this is the amplitude of the force. So the force varies with as an harmonic function, which we can write it as f naught sine omega t, where f naught will be our 24, omega is this 10. Okay, so t is the time variable. So in this case, the force acting on the system is 24 sine 10t. All right. So the stiffness of the entire system, 4 springs, so therefore 4 into 200, so you will have 800 Newton per meter. Then the natural frequency of the system is K over M. So here the M represents the total mass. Okay, stiffness is the total stiffness. So here the natural frequency of the system we can calculate as 5.16 radians per second. All right, so this is your F naught 24 newtons. Okay, so now you can straight away apply the required equations. Okay, so you can calculate the magnitude of the displacement. Okay, the amplitude we can write, I'm sorry. So X can be written as F naught over K. So F naught is the force which we calculated, 24. 800 is the total spring constant. So omega over omega L. So omega is, we know, 10 external frequency. Okay, natural frequency we calculated. Okay, so this is 5.16. So this will be your R, or we can also write it as omega over omega N. So you just use the equation and calculate, and you can see that the maximum amplitude or the maximum displacement is 10.7 mm. Okay, so this question is just calculating the unbalanced force. Then you know what is the external frequency of omega. Okay, so you can see omega, we can call it as the radial frequency or circular frequency, and omega is also rotational velocity. Okay. All right. Any questions on this, guys? All right, teaching. How about others? All right, Shasindra. Okay, then we look into another question. So this is again another question related to rotating unbalance. Okay, so here a counter rotating eccentric weight exciter is used to produce the forced oscillation of a spring supported mass as shown in here. Okay, this is by varying the speed of rotation, the amplitude is 6 mm was recorded. When the speed of rotation was increased considerably beyond the resonant frequency, okay, the amplitude approach reaches a fixed value of 0.8 mm. Okay, you are asked to determine the damping factors of the system. So you need to calculate the damping values for the system. uh, what is given is only the resonant amplitude and also the amplitude of the resonant during the resonant frequency. All right. So let us go through the working. So here the transmissibility you can write as capital M over small m into x over eccentricity. Okay, so this is the given transmissibility response for the rotating unbalance. Now for this, you can write now that this magnitude of the resonant amplitude X, okay? So ME, you can write, okay, over, here, resonance means omega is equal to omega n. So that means the ratio is 1. So omega over omega n is 1. So if you replace this with 1, so here this one will be 1. Okay, so this one is also 1. Okay, so what happens is this expression becomes 1 over just 2 eta, because 2 eta square under root will become just 2 eta. Okay, so that means during resonance conditions, so when resonance takes place, so this equation will be simply 1 over square root of 1 minus 1 square whole square. Okay, so plus 2 eta whole square. 2 eta into 1 whole square. Okay, so this one is simply boils down to 1 over 2 eta. Okay, so therefore you can write now X as only we write as X. Okay, so cross multiply and divide ME over M over 2 eta. So during resonance, the amplitude is given as 0.6 cm. Okay, so that means this ratio is 0.60. But again, we know the eta value. So eta value is given. Okay, the damping ratio is given. Okay. The amplitude appeared to be a fixed value of 0.mm. So when omega is very much greater than omega n, so this is another point given. So when the frequency is much greater than the natural frequency of the system, so what is given, that the amplitude is given as 0.08 cm. So now we have two equations. Okay, what is the amplitude here? We can just write it as mu over capital M. So that is 0.08. So now consider this is your equation 1 and this is the equation 2. So from equation 1 and 2, you can see that 0.6 is 0.08 over 2 into eta. So therefore you can separate eta and you can write eta as 0.08 over 2 into 0.60. So that gives you the damping ratio as 0.0666. So the damping ratio is quite low. So in this example, so the data given is quite less and the data refers to resonant conditions and the data refers to when the external frequency is much greater than omega n. So you are dealing the case of omega is much greater than omega n natural frequency. So for these two conditions, as we know amplitude, so we can write the first equation and we replace omega over omega n with omega 1 because it's the resonant conditions. And the resonant condition, the ratio of frequency R is equal to 1. Okay, so therefore we end up with equation 1. Then when omega external frequency is much greater than the natural frequency, we know the amplitude reaches 0.08 cm. It is given. So that means MU over M capital M is equal to 0.08. So from equations 1 and 2, then the only unknown is the um, damping ratio, which we can readily calculate. All right, so this is, you can expect these type of questions for forced vibrations with either base movement or with rotating unbalance. So we have done two cases now, the forced vibration with the base movement and forced vibration with unbalanced force for rotating masses. Okay, so in both the cases we can define okay, I think I'll just okay, maybe next lesson I'll give you the formulas in a consolidated format. Okay, so then the problem is to isolate this transmissibility. So reducing or isolating the transmissibility. So this is a very important part of design. So when you are designing a vibratory system, so we need to make sure that uh, any external forces, so the transmissibility through the system is minimized. Okay, so this can be done by we need to avoid this resonant conditions. Okay, so the first thing is we need to make sure that resonance conditions do not occur. Okay, and there is a controversy because when we talk about the productivity and the economical design, so the system should operate at high speeds. Okay, and you want to use the efficient use of materials. So sometimes when you are using high speed, so the resonant conditions becomes unavoidable. So to avoid the resonant conditions, then we need to study the system characteristic, and then we need to consider all the design factors, including the transmissibility ratios, okay, all the governing equations. So we have touched upon this and we discuss again. So you can see that in this plot, okay, so the transmissibility ratio versus the frequency. Okay, so this is for different damping ratios, for different damping ratios. So one is the condition of resonance when the frequency ratio is 1. So the amplitude of the displacement transmissibility becomes maximum. But when the value is equivalent to square root of 2, so you can see that the transmissibility, the displacement transmissibility becomes 1. Okay, so that means simply x is equal to y. Okay, so simply x is equal to y. So if you want to reduce displacement transmissibility, you need to make sure that omega is much greater than omega and natural frequency of the system. Okay, so this is where the omega is less than, much greater than natural frequency. So R is higher value, okay, greater than 2. So here you can see the transmissibility is less than 1. So the transmissibility is less than 1. So if you want to design a system where the transmissibility is reduced, so you need to make sure that omega is much greater than natural frequency of the system. And we know natural frequency of the system depends on the mass, depends on the stiffness. Okay. So just to sum up, so we need to minimize the transmissibility. So when omega is less than root 2 times, okay, natural frequency, so x by y is greater than 1, as you can see from the figures here. Okay, so for all values, x by y here is greater than 1. okay, for different damping ratios. When omega is less than omega n, okay, so when omega is less than root 2 times omega n. So similarly, when both are equal, omega is root 2 times omega n, so this ratio becomes 1. Okay? So when here you need to consider this root 2 separator. So this is root 2 times omega n. So there's a typo here. So omega n should be outside root 2. Okay, so when the external frequency is greater than root 2 times omega n, so the response, the amplitude x is less than input input amplitude y. So therefore, this will results into an isolation, which is a desirable case. So if you want to design a system, you need to make sure that the external frequency is much greater than natural frequency of the system. So then you'll be minimizing the transmissibility. So whether it is force transmissibility or displacement transmissibility, so you need to make sure omega is much greater than omega n. Okay. So the same thing is mentioned here. Omega over omega n is greater than 2, square root of 2. Okay. So this description is just we touched upon. Okay, so the transmissibility ratio we have shown, the force transmissibility or the displacement transmissibility. So here, this is the standard expression. Whether we are dealing with damped forced vibration due to base movement or due to unbalanced rotating force, either way, this is the equation is the same. Okay, then when the damping is negligible, so when eta is negligible, so when eta is negligible, then this transmission ratio, you can simply write it like this. So we can write this as 1 over, okay, rarely we use this equation, r square minus 1. So transmission ratio, transmissibility ratio is 1 over r square minus 1. So this expression can be written as 1 over r square minus 1 when eta is less. So when the damping ratio is negligible. All right, so this is a bit of point to be noted. Okay, so next we talk about the vibration measuring instruments. So these are all, there are different types of vibration measuring instruments. So for measuring earthquake waves, so we have, what are the measuring instruments? They are known as the piezometers. Okay, so essentially the system of any vibration measuring system will characteristically will have this type of setup. Okay, so where y is the base moment. Okay, so base moment is a function of omega, so it varies. Capital Y is the magnitude of the base moment or amplitude. So you have a damper, a mass, and a stiffness. Okay, the governing equations are exactly the same. Okay, the analysis is also exactly the same. So we can use the base moment of a vibratory system, okay, forced vibratory system, for measuring vibrations. So particularly if you want to measure the vibrations coming from the earth, okay, the piezometers will have a small force vibratory system having M, K, and C. Okay. The electronics part or the mechatronics part we will not discuss, but essentially all the equations, governing equations are exactly the same as the forced vibration with base moment. So I'll not go through these equations again because essentially they are the same. Okay, so the how the system is measured, the accelerometers or the piezometers, the depends. The mechanical system is not required for us, so we can avoid this. Going into the description of the measurement system and the hardware of the measuring systems. So that is not required. The last one which we can touch upon is this example. So focus only on this example. Now let us look at this. So a vibration pickup transducer is constructed with a mass of 10 grams. So you can see these are very minute instruments to measure the vibration. So the mass of the entire system is 10 grams and a spring of 50 Newton per meter stiffness. The damping ratio is 0.707. So for this type of setup, so what is the natural frequency of the system? So the natural frequency, we can write it as square root of K over M. So K is 50, M is 10 grams. So as you can see, the natural frequency of the system is 70.71 radians per second. Okay. Then the value of linear acceleration that produces a relative displacement of 2 mm. So here the displacement is given as 2 mm on the instrument. Okay, so when the displacement is given 2 mm, so you can calculate the acceleration is, we know that V is equal to R omega. Okay, so then acceleration is from V square over R. So the normal acceleration is V square over R. So you can say AM. So V is R omega. So V square is R square omega square. So this will become R omega square. So the normal acceleration. So you can write the normal acceleration the same way. Instead of R, we have here the Z, 2 mm given. So therefore, you can calculate the acceleration here. Okay, so from this expression, R into omega n square. So you can see the acceleration is 10 meter per second square. So for the displacement of 2 mm. Okay, so you're converting the 2 mm into meters per 2 meters. Okay, converting mm into meters. Then omega n we have calculated. So take the square of that. R into omega square. Okay, the next part is the usable range of the instrument is such that the error in the acceleration measurement is 1%. So here the error is 1%, so the amplitude ratio is 99%. Okay, so you can say that amplitude ratio is 0.99. Then we use the formula for the amplitude ratio. Okay, so from here we need to calculate the omega. Okay, so eta is given, damping ratio is given 0.707. So from this calculation, then you can calculate the square, R square. R square can be calculated. So therefore, you know R. So since you already know natural frequency, omega can be calculated. So this is the frequency with which, okay, the vibratory external frequency, okay, the system is receiving the vibrations externally with a rate of nearly 175 radians per second. Okay, so you can see that the vibration measuring instruments essentially works on the principle of the forced vibration with base moment. So all the expressions related to the base movement can be applied here. And yeah, and we know that the relationship of omega and omega n to reduce the transmissibility. So from for design consideration, we can say that omega should be much greater than omega n. So in quantitative terms, we can say that omega should be greater than root 2 times omega n, so that the transmissibility will be reduced, less than 1. And the transmissibility is highest for resonant conditions when R is equal to 1. All right. Guys, any other questions? Let me know. Okay. You can go through the other 2 questions here, so they are not difficult. Okay, there's another question you can go through here. Let me know if you have any questions related to today's theory part. Otherwise, I can move on to the second part of your assignment. Guys, any questions? I need at least few responses. I'm going to count how many says. Okay, Nuraza said, Shashi Bindran said. How about other? Okay, the thing is the Karya, all right, Daryl. Okay, how about others? We know, okay. So hope others are okay, Daryl. All right. Yeah, need to try out the question. So next I move on to the second part of your assignment. All right, so guys, look at this assignment and try to understand what is given. So this is for you to work out. I'll be just guiding you. So a harmonic force, a maximum value of 25 newtons and frequency of 180 cycles per minute, acts on a machine of mass 25 kilograms. Okay, so you are asked to design a support system for the machine. Okay, design means you need to find out the value of the damping constant and the stiffness constant, stiffness value, so that only 10% of the force applied to the machine is transmitted to the base supporting the machine. So that means, guys, you need to respond. What is the transmissibility given here? So what is the transmissibility, guys? Uh, 10%. 10% means, so 0.1. So the transmissibility should not exceed 0.1 as given. Okay, so the force maximum value is given 25 newtons. Okay, so that means so this is F naught. So maximum. So frequency, external frequency is 180 cycles per minute. So you need to convert this 180 cycles per minute into omega. So omega will be, so 2 pi f. So what is frequency? 180 cycles per minute. So how many cycles per second? Any answer? How many cycles per second? $180 cycles per minute. So convert into standard. So you can say it is 180 over 60. That's correct, Dichen. So that means this will be 3 cycles per second. So convert into radians, radial frequency. So 2 pi into f. So that is 6 pi. So this is 2 pi into 3. Okay. So 18.8 radians per second. So that will be the frequency omega. Okay. So you can 6 into pi. Okay. So pi, if you use 3.141, so I think you will get 18.8. All right. So the machine has a mass of 25 kilograms. Okay, only 10% of the force applied to the machine is transmitted to the base. So now we need to find out the design parameters for this. Guys, can you copy the equation for transmissibility? So as I know, the transmissibility expression is 1 plus. So if I write like this, it may not be very nice. So, but follow 2 eta r square over 1 minus r square So make sure you write the equations correctly. Okay, plus 2 eta r whole square. Okay, the entire thing is under square root. Okay, the whole thing is under root. Okay, so r is equal to omega over omega n. So can you calculate omega n? Omega n will be square root of k by m. So can you calculate omega n and then r? Let me know. Now, so in fact, we don't know k, m, okay? So we can't calculate natural frequency. So we need to find out k value, okay? So we can use r as omega over omega n. So now to get a transmissibility of 0.1, I think I will use the camera for. Okay, so given transmissibility 0.1, okay, so we can write 0.1 is equal to, okay, 1 plus 2 eta r whole square, this plus 1 minus r square whole square plus 2 eta r square, the whole under root. Okay, so here, how many unknowns are there? So there are two unknowns. So we don't know the damping ratio, and also we don't know the R, the ratio of frequencies. So this equation cannot be solved. Okay, but this can be solved based on some assumptions. Okay, now let us choose. So a low damping ratio of 0.1. Okay, and solve equation 1 above. Okay, so now we assume that the damping ratio for the system is 0.1, and then we use 0.1 to evaluate or to solve this equation. So that means to find out the damping ratio. So we can write 0.1 is equal to 1 plus 2, instead of eta, I take it as 0.1. So I can write 2 into 0.1. Guys, solve the above to find R. I'll wait for your answer, guys. Oh no, Darren, I think you need to try again, check again. How long when 3.655, that sounds to be okay. So you can take square both sides, so you can write 0.1 square is equal to, so you can write 1, so this becomes 0.2 r square over 1 minus r whole square plus 0.2 r square. Okay, so solve this to find out r. Now, without taking the square root, it is difficult to solve. Uh, any other answers? How long is giving 3.655? So I want some others also to confirm the answer. So I'd like to know if any other will confirm the answer. Okay, Shaswindran also giving 3.655. So therefore, you will be able to solve. So when you submit your assignment, to give all the steps. Okay, so you can say R is 3.655. So we know R is nothing but omega over omega n. So this is omega over square root of k by m. Okay, so that means you can say that r square is equal to omega square over k by m. Okay, so you can write k is equal to m omega square over r square. So you can use this formula to calculate k. So the spring constant. So can somebody give the answer for this k? (665 units). So what are the units? Yeah, that's correct. So you will be getting about 665 newtons per meter. Okay, so we need to calculate then the damping constant. So the damping constant C will be so you can use any of the formula which you know. So one of the formula is 2 eta square root of Km. So you can use this formula to calculate the damping constant. So any answer for C? Daryl says 25.78 units. Okay, you can also say Newton second per meter. You can also say kilogram per second. Okay, the better way of writing is Newton second per meter. All right, so this will be the solution. And as you can see, the entire working depends on the choice of the damping ratio. So if you choose slightly a different damping ratio, then your answers will be different. So the central point of this problem is, so the designing depends on the the choice of your damping ratio. So generally we expect the damping ratio to be on the lower side. So choosing a value of 0.1 is logical for this problem, for this type of problems. All right, so this will be the complete solution for this question. Any doubts? All right, so next I move on to the second question. Okay, so let us go through this question. So the mass is given. So a machine has a mass m is equal to 70 kilograms. Is mounted to ground through an isolation system of total stiffness. So the K value is given. With the measured damping ratio of 0.2. So the eta value is given, the damping ratio. The machine produces a harmonic force of 450 newtons. So this is the magnitude of the force. So you can take this as F naught at 13 radians per second. So this is the external frequency omega. Okay, under these conditions, and the machine is operating in a steady state. Okay, so determine the amplitude motion of the machine. So amplitude of the motion of the machine means you need to find out the x value. So what is the x value? Then the phase angle of the motion. So you need to calculate the phase angle phi. And the transmissibility ratio C. So you need to calculate the transmissibility ratio TR. And the maximum dynamic force transmitted. So the maximum dynamic force transmitted is the force transmitted, FTR. Then the maximum velocity of the machine. So you need to calculate Vmax. So Vmax is simply, we know from the first session, the Vmax is equivalent to omega into amplitude x. I can write x max. So maximum amplitude. Okay, so these are the 5 things we need to calculate. So guys, you can calculate what M is given, K is given, so you can calculate the natural frequency of the system. So you can calculate the natural frequency. So what is the answer for the natural frequency? Uh, 20.7 radians per second, correct? So 20.7 radians per second. So omega is given as 13 radians per second. So you can calculate R. So R is the ratio of frequencies. So omega over omega n. So how much you get ratio of frequencies? So 0.628, correct, Azhar? So you get 0.628. All right, I'll move to the camera. So we can write amplitude x is equal to so f naught over k, then 1 minus r squared whole square plus 2 eta r whole square under root. So x is the amplitude of motion. So can you calculate this? Because all the quantities are known. F naught is given, K is given, R we calculated, eta given, so everything is given. So therefore you can solve this and find out the value of the amplitude. So let me know any answer. So calculate amplitude. So Michael is giving 0.02288. Any other answers? So I want at least another 2, 3 students to confirm this answer. No, sir. I think. How about any other answer? So at least another 1 or 2 answers. No, sir. You can check your answer again. It's not correct. Yeah, that's correct, Shashivendran and Eva and Michael. So you will be getting about 0.0229 the units. So you must tell the unit. So you're measuring amplitude. Amplitude will be meters. Oh no, meters. Newton is force. All right. So next you need to calculate the phase angle. So to calculate phase phi. So phase phi, you can write the expression for phase phi. You can refer tan inverse of 2 eta r over 1 minus r square. So you can use this expression to calculate the phase. $25.52 the unit. Yeah, the degrees you can say. So it will be 22.5 degrees. You can also give in radians. So this is equal into how many radians? How many radians? No. 180 degrees is equal to 2 pi radians. Okay. So 22.5 degrees is equal to how many radians? Sorry. Yeah, 0.393. All right. Okay, so the part B is settled. Next, part C. So part C, you need to calculate the transmissibility ratio. Okay, so I just give you the equation. You can calculate 2 eta r whole square over 1 minus r whole square plus 2 eta r whole square, everything under square root. So calculate this. Yes, Heva, you can answer give in both degrees and radians. Both answers are okay. All right. So, any answer for the transmissibility ratio? 1.49, very close, but not correct. You can check your answer again, Azir. Heilong is giving 1.57. That's correct. So the answer is 1.57. So that means the transmissibility ratio is greater than 1. So you can see that more displacement is transmitted. All right. Then we calculate the next part, the magnitude of the force transmitted. So you can write the force transmitted is so transmissibility ratio into the force. So the amplitude of the force given is 450 newtons. So you can say 1.57 times 450 newtons. So how much you get? That's correct, Michael. So you get about 707.6 newtons. So this is the force transmitted, which is greater than the amplitude of the force. Then the last part of the question is you are asked to find the maximum velocity. So the maximum velocity. So the maximum velocity, we can write it as omega into x maximum. So that means omega into amplitude x. So we know both omega and x. So the amplitude you calculated part A. Okay, so omega is given, right? Omega is given as 13 radians per second. So calculate the maximum velocity. uh, 0.296 meter per second. That's all right. So you get about 0.29 meter per second. Okay, so this is how you can solve that question step by step. So let me know if you have any questions or any doubts. Okay, so all the 5 parts of the question calculated. All right, so next we move on to the third question. Okay, so read the question and write down whatever all the given information. Okay, a large industrial exhaust fan is mounted on a lightly damped steel frame. Okay, so lightly damped steel frame. So this is uh, the description given. So for steel frames, it means that the damping ratio is small. So eta is small. So when it says light damped steel frame means we can take it as the damping ratio is small for the steel frame material. Okay, the plant manager has decided to mount a storage bin on the same platform. Adding mass to a system can change its dynamics substantially, and the plant manager wants to know if this is a safe to change this particular make. Okay, the original design of the fan supports the system is not available. So he doesn't have any knowledge about the spring constant or the damping ratio, so no details are available. So therefore, measurement of the floor amplitudes are made at several different motor speeds in an attempt to measure the system dynamics. So the response of the system was measured under variable frequencies. Okay. No resonance is observed in running the fan from 0 to 500 RPM. So no resonance. So no resonance is observed in running between 0 to 500 RPM. Okay, deflection measurements are made and it is found that the amplitude is 10 mm at 500 RPM and 4.5 mm at 400 RPM. So when the rotational speed is 500 RPM, the amplitude is 10 mm and it is 4.5 mm at 400 RPM. So the mass of the fan is 50 kg and the plant manager would like to store up to additional 50 kg on the same platform. So the best operating speed for the exhaust fan is about 400 to 500 RPM. So this is the best operating speed for the exhaust fan. So depending on environmental conditions in the plant, is it is it advisable to the manager to add this storage bin on the same platform? So if not, what is the mass that can be added safely? So justify your reasons. Okay, so read the problem, try to understand what is given. Okay, so the first point for this is that the exhaust fan is mounted on a lightly damped steel frame. Okay, so for a lightly damped So damping ratio is very less. So when damping ratio is less, we can write. So we can write the transmissibility ratio X over Y. So the transmissibility ratio X over Y can be written as 1 over 1 minus R square. So you can ignore eta value, and the transmissibility ratio formula reduces to X by Y is equal to 1 over 1 minus R square. All right. So this is the hint to solve this problem. All right, so now the time is nearing 10:20. So we'll stop and continue this next week. Let me know if you have any other questions. So let me know any questions. Because we can't solve this in the next 10 minutes. Guys, if you have no other questions, then we'll stop here. Then we'll continue next session. All right. So I'll see you next week again. Okay.